Okay, good morning, everyone, again. Thank you for joining us today for our webinar on microfiltration membranes. We're excited to get started and hope everyone will find the information interesting and educational. Before we get started, I'd like to introduce Steve and myself as the speakers for today's webinar. Steve Doolin is an application engineer here at Sterlitech and comes to us with over 2 decades of industry experience. He's got great insight into microfiltration membranes, their applications, and process engineering, which we're lucky to be able to leverage in order to help our customers achieve their research goals. You may have also chatted with Steve on our website. My name is Molly Harris. I'm a product manager for our microfiltration line. I come from a background in lab science and got my master's in microbial biotechnology from NC State University. At Sterlitech, I work to make sure that we're supplying products and tools that help our customers stay at the forefront of their fields. To provide a little bit more information about Sterlitech, we were founded in 2001 by Mark Spots around a unique silver membrane filter product line. And since then, we've grown quite a bit. We now offer over 2,000 products focused on filtration, and our headquarters in Kent, Washington have expanded to an office, manufacturing, and warehouse space. So over the 18 years that we've been in business, we've grown from 4 to over 30 people, and we're looking forward to continued growth in the upcoming years. Our mission is to equip scientists and visionaries with the filtration products they need to turn ideas into reality. So with that covered, we can move on to what we'll go over in the presentation today. We'll start with some basic concepts of microfiltration membranes, what they are and how they work. Then we'll move into looking at some characteristics to consider when you're deciding what filter material might be right for your application. After that, we can look at different formats that membranes are purchased in and end with a Q&A session. So I encourage you to type your questions as they come up throughout the presentation, and then we'll have plenty of time to address them at the end. So from here, I'd like to hand it off to Steve to get us started.
Hello, Molly, can you hear me?
Yes, we can hear you now.
Oh my gosh.
We're worried about you.
Uh, that's I apologize for that.
Okay.
Thank thank you for joining the webinar today. My name is Steve. As Molly said, I have quite a bit of experience with microfiltration membranes, and I hope to keep this entertaining and informative. With that, we'll move on to our presentation. So what are microfiltration membranes? Basically, in their most simplest concept, they are thin sheets with open microporous pore structures. With the design that they're allowed fluids to pass, or able to allow fluids to pass while retaining suspended particles. Membranes themselves can be manufactured from a wide variety of materials, and these can include both inorganic materials such as metals and ceramics, and polymer materials, which are very wide ranging, including nylon, PVDF, PES, and so on. So we can discuss a little bit about how the membranes work. And in a more basic construct, let's talk about microfiltration. So microfiltration is basically the retention of suspended particles from a fluid after passing through a physical barrier. Microfiltrations typically doesn't affect the dissolved substances within the fluid, although there are certain exceptions. The retained particles, it's called microfiltration because the retained particles are typically around the size of 1 micron or 1,000th of a millimeter, plus or minus about an order of magnitude. The membranes themselves are operated usually in normal flow or dead end flow so that the entire fluid stream passes more or less perpendicularly through the membrane, and the fluid that passes through the membrane to the downstream is called the filtrate, while the particles retained on the upstream surface or within the membrane are called the retentate. We have a diagram here that shows a physical representation of what's occurring. It's just important to note in the diagram that the size of the particles are greatly exaggerated to display the concept. In reality, the particles are usually smaller than the thickness of the membrane. So we can discuss a bit about how membranes work and what the particle capture mechanisms are. Of course, most of you realize that particles larger than the pores are retained directly by physical processes, which are called mechanical retention or size exclusion, or direct interception. These are all used interchangeably. And the particles, because they're larger than the pore openings, are physically unable to pass through the pores. There are some concepts about particle retention that could be interesting. So size exclusion can also be aided by particle agglomeration if the particles have a tendency to stick together. When it occurs at the surface of the membrane, it's sometimes also called sieving. And it can also occur within the membrane structure, not necessarily at the surface. This is especially true for asymmetric membranes, such as mixed cellulose esters or polyether sulfone, which have much larger pores on the upstream surface. And for the most part, size exclusion is unaffected by process conditions, especially for rigid and single particles. Now, in addition to mechanical retention or direct interception, there are also adsorptive retention mechanisms in which particles that are small enough to enter the pore structure are able to be retained by adhering to the pore walls. The adsorptive retention is primarily dependent on the membrane material itself and how it interacts with the particles, and as a result of charge interactions, hydrophobic interactions, and also inertial impaction. Some common examples of adsorptive retention include binding of large organic molecules like proteins, nucleic acids, and endotoxins, and to membranes that are slightly positively charged, say like nylon or nitrocellulose. The adsorptive retention mechanisms can be affected by process conditions, including differential pressure, temperature, the solution chemistry like ionic strength or pH, and also the viscosity of the fluid. And these conditions can actually enhance or reverse the adsorptive retention. For example, when filtering gas or air streams, due to the ultra low viscosity, inertial impaction becomes the dominant capture mechanism for microporous membranes. So we can discuss a few microfiltration membrane applications, certainly the most common microfiltration membrane applications. One of the most common is simple clarification or particle removal from samples. And these samples might be for filtrate analyses, it might be reagent purification. As we listed here, one of the most common applications is preparation of chromatography samples so that they don't clog the chromatography columns on the instruments. And it may also include filterability testing and scale-up studies. Another application or common application is filtration for bioburden reduction, where the membrane is used to retain microorganisms that are present or potentially present in the fluid. And this could be to actually reduce the amount of microorganisms in the fluid, or to remove the microorganisms completely. For example, tissue or cell culture media is commonly filtered through a 0.2 micron rated membrane to remove all bacteria so that the cultures aren't contaminated. Another common application is filtration for analyses of the particles that are retained on the membrane surface. And it's important to realize that these particles could also be microorganisms or animal cells as well. A common application within our product line is actually for the unique silver membrane that we offer is for analysis of environmental samples that may contain crystalline silica, as shown on the slide here, and also asbestos. The silver is kind of fun in that regard because it's suitable for well suited to SEM and X-ray diffraction studies. Another common application is cell culture substrate. Commonly, these are the track etch membranes, so polyester track etch or PVP-free polycarbonate track etch. And the membranes are actually used not as a filter, but as a porous substrate to allow cells to grow on the surface for attachment-dependent cultures, while allowing some access to nutrients through the pore structure. And microbial detection is another common application, and this is where the membrane, the retentate, is studied to see if there are microbes present and also to enumerate the amount of microbes present. The most common method being the EPA membrane filter or MF technique, where coliforms are captured on the membrane surface and then subsequently cultured into macroscopic colonies that can be counted. Additionally, track etch membranes are used for elution techniques that look for Legionella, Listeria, schistosomes, and other pathogenic organisms. And finally, we mentioned venting and degassing, and hydrophobic membranes are well suited for venting applications. And they're also suited, not mentioned here, but also commonly used for membrane distillation as well. And some applications that we didn't mention, but are niche applications that are kind of interesting, is that some microporous membranes are used in specialized nucleic acid and protein blotting procedures. And some track etch membranes have been studied as templates for synthesis of nanorods. So let's consider some membrane characteristics. Sterlitech actually offers a very wide variety of membranes. And as you can see in these representative SEM photographs, there's a wide variety of structures to these membranes as well. And interestingly enough, these structures are results of the materials and the manufacturing techniques used for these membranes. For example, the inorganic membranes, such as the ceramics, are typically manufactured by sintering, where agglomerations of particles are bonded together using process conditions. Another example is the PTFE membrane, which is on the bottom row in the slide here, and that's formed by a unique process where the PTFE particles are sintered together and then expanded. They're stretched in biaxially direction in two directions to form this unique node and tendril structure of the pore structure. Most of the other polymer membranes you see in the list here are formed by solvent cast technique, where the polymer is dissolved in a solution and then spread out into a thin liquid layer. The thin liquid layer is then, through the addition of non-solvents or changing process conditions or both, causes the plastic to precipitate by phase inversion out of the solution to form the foamy pore structures that you can see in these pictures. These foamy structures have tortuous paths to retain particles. And curiously, they also are highly interconnected. And interesting aspect of these membranes is that they can exhibit significant lateral flow by capillary action. And also that these membranes themselves can have some variation in structure. They can be symmetric or asymmetric, and they are sometimes manufactured with an external or encapsulated nonwoven support layer. And I do want to point out one more membrane type on here. That's the polycarbonate track etch and polyester track etch membranes. You can see them as PCTE or PETE in the slide. These membranes are actually very unique in that they're thin, solid films with randomly distributed cylindrical pores. And they're manufactured in a process that actually is a two-step process where you start with a non-porous film that's exposed to accelerated heavy ion particles that are passed through the film that form the ion tracks. These tracks themselves are not holes. They're just areas where the membrane structure has been disturbed. The film is subsequently exposed to a solvent bath that etches the tracks into approximately cylindrical holes. And the pore diameter is controlled by the conditions and exposure time in the solvent bath. But the interesting result is that you end up with a very almost two-dimensional pore structure with an exclusive sieving retention mechanism where most particles are retained on the surface of the membrane. And that uniquely lends those membranes to being used for study of retentate, microscopic study of the retentate. So we can consider some membrane characteristics for selection. And the first one is wettability of the membranes. And that simply refers to how the membranes interact with water. So the hydrophobic membranes, if you apply water to their surface or a small amount of water to the surface, repel the water, and the water tends to bead up as droplets, rounded droplets. And it's interesting behavior in that you have a porous surface, but it's still able to repel the water. And that actually occurs because there is the capillary action, or the interaction between the water and the air in the pore structure, is causing the repellency. Hydrophobic membranes are typically used for air and gas filtration and venting, and that's because water-filled pores do not allow the bulk flow of air. So hydrophilic membranes are just the opposite. When water is applied to their surface, the water is spontaneously drawn into the pores and saturates the membrane. And this is also by capillary action, but it's because the water has a different affinity for the materials of the membrane structure. And hydrophilic membranes are, as you might suspect, used for filtering water and aqueous solutions because they easily wet the structure and pass through the membrane. Here's a small video for you to demonstrate hydrophobicity and hydrophilicity, I guess we'll call it, of the various membranes. You can see an example of a hydrophobic membrane on the right is PTFE. And then we have an example, and you can see how the water beads on the surface when it's applied and is repelled. And then on the left, we have a hydrophilic cellulose acetate membrane. And you can see then the water is applied, it spontaneously wicks into the membrane structure. And both are caused by capillary forces. And you'll notice that the appearance of the membrane changes when the pore structure is wetted. That's because the liquid has a different refractive index than the air that's in the pore structure that's being displaced. So within our product line, we offer both membranes that are hydrophilic and hydrophobic, and there are actually some membranes within our product line that can be offered in either condition. For the PTFE and PVDF membranes, these membranes are inherently hydrophobic, but we do offer hydrophilic versions that have been chemically treated to either coat or modify the surface. The polyester track etch membrane, on the other hand, is hydrophilic, and we offer a version that's been treated to render it permanently hydrophobic, and it's used for venting applications that are tolerant to gamma sterilization. And the PCTE is a bit unique in that while it doesn't technically have a water contact angle greater than 90 degrees, it is functionally hydrophobic. It's close enough that it's very difficult to wet. So the PCTE is available in a hydrophilic version that's been treated with a material called polyvinyl pyrrolidone to reduce its water contact angle and improve wettability. So another concept or a characteristic of membranes to consider when selecting is pore size rating. The pore size rating provides an idea of the size of the particles that will be retained or repelled by a by a membrane via size exclusion. The rating is almost always designated in micron or micrometer units, and these are that's 1/1000th of a millimeter. And the membranes can be designated as a nominally rated or absolute rated. Absolute ratings are typically an indication of particles, of the smallest particles that are expected not to pass through the membrane. And when membranes are characterized using particles, the practically defined absolute is 99.9% efficiency or better. When the retention is characterized using microorganisms, which is commonly used for 0.1, 0.2, and 0.45 micron pore sizes, absolute implies that there's a complete retention of a particular microorganism used to define the pore size. And by complete retention, the filtrate is studied to make sure that it doesn't have any bugs. So most membranes that we offer are actually available in a wide range of pore size ratings to allow them to be optimized for applications. And just to give you a feel of the micron sizing or scale, here we have some examples listed of various common materials and how they correspond to the micron scale. So you can see that fine beach sand is about 1,000 microns or 1 millimeter in diameter, and that's fine beach sand, like the powdery beach sand, not coarse beach sand, which is even much larger. Human hair, the diameter of a human hair is about an order of magnitude smaller, around 60 microns. And then you can see that red blood cells and asbestos particles are yet another order of magnitude smaller, around 5 to 8 microns. And that also gives you an indication of why asbestos is such a dangerous material to inhale. And then finally, bacteria, at least the smallest bacteria, are another order of magnitude smaller. It's conventionally thought that most bacteria are about 0.2 micron or larger. So we have a graphic representation here of the pore size rating availability for our hydrophilic membranes. And as you can see here, some membranes are only available with one rating, like the PAN, and some membranes have a very broad rating, like the polycarbonate track etch, which ranges from 0.01 to about 30 microns. And you can see that conventionally the microfiltration range is about 0.05 micron or so to about, it actually would range up to about 5 to 10 microns, but we show a little narrower here. There are other processes for separation beyond microfiltration that I might briefly discuss, including ultrafiltration, nanofiltration, reverse osmosis, which go to the smaller end of the scale. And these are typically used to retain dissolved substances instead of suspended solids, like the microfiltration range. And then you have particle filtration on the other end of the spectrum, which just basically means you're retaining larger particles. There are material used in addition to membranes in the microfiltration and particle filtration range that includes cellulose filter paper or glass fiber and polymeric nonwovens. These materials can do overlap the microfiltration range, but they usually have inherently larger and less uniform pore structures than microporous membranes, and usually have less precise retention and less stringent pore size ratings. And we have the same graph that shows the availability of the pore size ratings for our hydrophobic offering as well. And you can see they're a little less broad than the hydrophilics, but they do cover the entire spectrum of the microfiltration range. And with that, I would like to hand back off to Molly, and she'll be glad to discuss with you filter sizing and formats for the membranes.
All right, thank you, Steve. Now that we've reviewed the filter materials, we can look at the different commercially available formats. The most typical format we see is pre-cut membrane filter discs. These are sold in standard diameters, so they're suitable for use with common vacuum and pressure filtration holders, like the vacuum manifold you see on the left here, or the inline pressure holders you see on the right. So some standard sizes are 13 millimeter or 17 or 25 millimeter diameters. And the table here gives you an estimation of the process volumes that you might be able to filter with those sizes. So for example, using a 25 millimeter disc to filter up to 100 mils of solution. Of course, the specific process conditions and fluids will impact this quite a bit, so these values are just to provide a general estimate. But something to note here is that though these diameters are the most frequently used, we do have the potential to custom cut membranes to unique sizes. So if you'd like to explore custom options or unique sizes for your applications, that's definitely something Sterlitech can consult for on those projects. A couple other options for membrane formats are to buy them as syringe filters or capsule and cartridge filters. These are membranes that are encapsulated in a plastic housing. So for syringe filters, it's a flat membrane disc that's contained in a housing with convenient fittings to adapt to tubing or a syringe. These are typically used to filter small sample volumes, such as HPLC samples. And they're meant to be single use for the most part, and we do offer pre-sterilized options. One potential drawback or limitation to using syringe filters is that the membrane is not easily accessible, so they might not be suitable for applications when the retentate on the filter surface would be needed for downstream use. The other product options to go over are capsule filters. In these products, the membrane inside the housing is pleated, so this increases the surface area and allows for larger process volumes and continuous flow applications. Capsule filters are not available in all membrane materials because some materials don't lend themselves well to the pleating process. But I would note that with both of these additional product lines, we do have the capability to explore custom options as well. This diagram gives you an idea of the commercially available membranes for syringe and capsule filters in terms of which membrane materials can be integrated into the housing, and then which membrane materials can be pleated and folded to be integrated into a capsule filter. So you can see glass fiber, nylon, PES, polypropylene, and PTFE are good for both of these. So we've reviewed quite a bit of information in a short amount of time, but just to go over the main takeaways for considering membrane filters, we would first recommend evaluating your retention requirements to help identify the appropriate pore size. Then it's important to evaluate chemical compatibility from interactions with aqueous solutions, as we discussed in terms of wettability, but also compatibility with the other chemicals present in solution, protein affinity of the membrane, and the temperature and pressure conditions of the filtration. Finally, you can consider which membrane format will work best for your sample volume and flow rate requirements. So throughout the process of evaluating and considering materials, Sterlitech is here to help. Our goal is to provide resources for our customers, and you can take a look at the resources page for membrane disc filters on our website, which includes a selection tool for common applications. For your initial evaluation of membranes, we do also offer small sample packs for purchase to get started, and our experts are here to answer questions over email, phone, and website chat. So with that, I'd like to take a moment and allow everyone to enter any questions that have come up throughout the course of the presentation, and we can start the Q&A session with Steve shortly. Thank you for listening. So we have one question to get started. Will the presentation be available to attendees? I can take this one. Yes, we will be sending out a recording within 24 hours with this presentation. All right. So let's see. The next question, Steve, if you're ready.
Sure.
Okay. We have a question that says, I encountered an interesting problem. I'm using PureMem 600 to clarify my solvent with 200 Daltons. I want the solvent to go through, but it won't go through. Do you have any idea, Steve, on why a solvent of 200 Daltons wouldn't go through a PureMem 600 membrane? And to clarify, this is in the realm of microfiltration, correct?
This is actually, I think the pure membranes are ultrafiltration, so it does go beyond my expertise a bit. I do understand a little bit about the Duramem and Puramem membranes, and my understanding is that the solvents do contain water or an aqueous solution that does reduce the permeate flow considerably. It would be important to make sure that you're operating in the recommended pressure range as well, which might be a bit higher than what you're expecting. I would recommend that you follow up with us by email at sales@sterlitech.com, and I can get you the cross-flow application specialist, Kenson, or our application engineer, Sarah, to follow up with you.
Yes, thank you. Another good question, does the surface roughness of your membranes affect the contact angle, such as in Wenzel or Cassie Baxter cases? If so, how do you characterize the true contact angle and wettability of the membrane?
Yes, that's a good question. I would expect the surface roughness to affect the contact angle somewhat. However, for most filtration applications, it's not really a consideration, so we haven't characterized that effect. For us, in most applications, it's simply sufficient to note whether the membrane repels water or is spontaneously wetted. So it's mostly either or. It's not or pass fail, if you will. We're not looking at the details about the exact water contact angles. And I suppose you could look at that, and that we do look at it indirectly in terms of membrane characterization around bubble point and water entry pressures, which might be affected. But those are concepts that we really didn't cover here, and they're a little more subtle. So if you'd like to follow up with me more about that, certainly send me an email. But the short answer is that we really haven't characterized the contact angles beyond noting that the membrane repels water or is spontaneously wetted by water.
Okay. Next question is, can you provide roll stock of membranes for OEM applications?
Yes, we actually do provide roll stock for a variety of our membranes. I had to note that some membranes aren't available as roll stock because of their manufacturing process or their physical structure. And what I'm thinking specifically is the inorganics, like the silver, the ceramic, and the alumina oxide. They simply can't be rolled into. They can't be provided in a rolled format. But most of the polymeric membranes we do offer as rolls for OEM manufacturers.
Thank you. What is the largest 0.2 micron filter available for process water filtration?
Yeah, that's something in our product line we focus on laboratory applications or small scale applications. So our largest conveniently available filter would be a 10-inch subassembly in a capsule filter, which is suitable for continuous flow of about, say, 3 to 4 GPM maximum. For larger filtration applications, you'd want to use a cartridge filter and a appropriately sized housing. We don't really specialize in that range of filtration or in process filtration, but we can certainly help you if you want to reach out to me. I'd be glad to provide some guidance. In my previous role, I did do a lot of work in that area.
Great. Okay. Can you comment on pore size rating test methods? I know you
Sure.
can.
Yes, I can. It's actually it's really interesting because characterizing retention of microfiltration membranes is actually quite difficult. Um, Historically, the 0.2 and the 0.45 micron pore sizes were actually defined using a retention of particular organism. For the 0.2, it's Pseudomonas or Brevundamonas diminuta, and for the 0.4, it was Serratia mersicens. And that refers to an ASTM method, F838. And absolute retention of either of those microorganisms was defined as that pore size. So if you had a membrane that absolutely retained P. diminuta, then it was defined as a 0.2 micron pore size membrane. Beyond those two pore sizes, it gets very subtle, and there's actually no consensus in the industry about how to characterize membrane retention. There were attempts, particularly ASTM F78 or 795, I think it is, or it might be 785. I think it's F795, excuse me. That attempted to define methods, but actually were so broad they weren't practical, and as a result, they were actually abandoned without replacement. So there are currently no standard methods to characterize membrane pore sizes. Most manufacturers end up using suspensions of particles like ISO fine test dust or coarse test dust or a mixture of both in purified water, and they'll use particle counters to attempt to characterize retention of their microfiltration membranes and media as well.
Great. That's very interesting. Next question would be, do strong acids reduce the effectiveness of various filter materials?
Yes, you have to be. We didn't discuss it much in the meeting, but you do have to be concerned about chemical compatibility of the membranes with the fluids they're in contact with. And some membranes aren't compatible with strong acids. In particular, nylon, for example, is dissolved by strong acids. So if you attempted to use a nylon with a strong acid, obviously, if it dissolved, it would be very affected by the liquids. We're certainly glad to help you evaluate chemical compatibility with your applications. You can simply reach out to us at sales@sterlitech.com, and we'd be glad to help you. In practice, there are a lot of online published data about compatibility of common engineering plastics that are used to make these membranes with common solvents. And while we don't necessarily have testing what we've performed ourselves, we are able to mine this data and make educated guesses about how membranes would be compatible with these fluids.
Great. We have another question. In a research paper, I often see the term scaling of membrane. Can you explain what that term means?
Sure. Once again, we're getting out of the microfiltration membrane realm. Scaling typically refers to RO membranes or reverse osmosis membranes. And those membranes are operated such that they're actually repelling ions, salt ions. And what can happen is that the salt ions can accumulate, or the metal ions can accumulate on the upstream surface of the membrane. And if they're not swept away by crossflow, they'll actually precipitate out of solution and coat the surface of the membrane. And that coating is called a scale. And if it happens in the membrane, it's called scaling, or the membrane has been scaled. And it significantly reduces the permeability of the membrane. And depending on the nature of the scale, it can be very difficult to clean off the surface.
Great. Okay. Is there any membrane which can be used for ethanol-based solutions?
Oh, sure. There are a wide variety of membranes that can be used for ethanol. Polypropylene and PTFE come to mind immediately. And you might be saying to yourself, well, these are hydrophobic membranes, so would they repel my solutions? And it would depend on the concentration of the ethanol. If the ethanol is, say, more than 50%, if the solution is more than 50% ethanol by volume or mass, either one, then I would guess or estimate that hydrophobic membranes would be easily wetted by those solutions, and you could use them. If it's mostly water, then you could look at membranes. I believe nylon has pretty good compatibility with low molecular weight alcohols.
Great. What is a membrane that can be used for an application at 150 degrees C?
Yes, elevated temperature applications are very challenging for the plastic or the polymeric membranes. We do offer the inorganic membranes, silver, alumina oxide, and ceramic, that all have very high compatibilities with very high elevated temperatures. So you might want to consider one of those. It depends on what pore size requirements you have and what flow rate requirements you have. Those membranes are quite expensive, and so you wouldn't want to use them without needing to. In addition, if your pore size requirements are less stringent, most glass fiber media are easily able to withstand that kind of temperature range.
Great. Does the thickness of the membrane change with pore size and type of membrane? And part two to that would be, would that affect the flux of the membrane with the same pore sizes?
For some of the membrane types, the thickness doesn't change or changes little with the pore size rating, and that would be the solvent cast membranes and the PTFE, the expanded membranes. The track etch membranes, there is some variability between thickness and pore diameter, and it's more a result of limitations from the manufacturing or inherent characteristics of the manufacturing technique. That said, I don't expect the pore size rating to influence flexibility that much, although for some membrane types, say like the mixed cellulose esters, the larger the pore sizes, the less strong the membrane becomes in general. So tensile strength might be an issue depending on how the membrane's handled. And some membranes fold better than others, or inherently more flexible than others. For example, PES and nylon fold quite well, while the mixed cellulose esters tends to crack when you fold it.
Interesting. Steve, do you know off the top of your head which membranes are gamma sterilizable?
For the most part, the majority of the membranes are gamma sterilizable, with the exception of the PTFE. So the PTFE membrane is not gamma tolerant, and the polypropylene membrane is not gamma tolerant as well. And you might notice that those are the two primary hydrophobic membranes that we offer, and it can be a real challenge to find a gamma tolerant hydrophobic membrane. And for those applications, we offer the hydrophobic treated polyester track etch membrane, which is gamma tolerant.
Great. Okay, let's see. This one's sort of specific. Would a microfiltration membrane retain silica nanoparticles suspended in alkali?
It's as long as the particles are larger than the pore structure, but once you get into the nanoparticle range, it becomes challenging to find microporous membranes that have small enough pores to retain them. Depending on the concentration of the particles and what study you're trying to perform, there are some track etch membranes that extend down to as small as 0.01 micron that might be able to retain them. That said, that membrane has very low intrinsic flow, and it would be probably would be clogged very quickly by that solution. If you want to, it might be good for us to follow up by email with that person as well.
Okay.
Yeah.
Okay, another question. Thank you everyone for your great questions, by the way. Keep coming in. So are hydrophilic PTFE membranes just as good as hydrophilic PES or PVDF when it comes to steam sterilization?
That is a good question.
It's a tough one.
We do offer one hydrophilic PTFE membrane within our offering, and that's sourced from Advantech, and we list it as Advantech hydrophilic PTFE membrane. That membrane is actually not tolerant of high temperatures, so it can't be steam sterilized or autoclave sterilized. At temperatures above 100 C, the hydrophilic treatment is affected, and the membrane reverts back to hydrophobic. I don't know how competitive PTFE membranes are rated, or how much temperature they can withstand, but my instinct is that that might be a common issue with the hydrophilic treatments used on the PTFE membranes. On the other hand, the hydrophilic treatment used on the PVDF membrane is very stable, and that membrane has a long history of being able to be autoclave sterilized. And I can't recall what the third membrane was, Molly. What was it?
PES, PVDF.
Yeah,
Those are
PES.
just those two.
PES is also very, very tolerant of autoclave sterilization.
Okay. What pore size is required for liquid sterilization and spore bacteria retention?
So commonly, it's 0.2 micron pore size as an absolute rating is used for is accepted by the industry as providing sterile filtrate regarding retention of bacteria. That said, there are viruses and bacteriophages that are smaller that can't penetrate the 0.2 micron pore size. So if those are a concern as well in your application, you may have to find a smaller pore size rated filter.
Okay. We had a question about slide 16, what the device on the left is.
Yeah, that device is, we call it a manifold, which simply allows you to operate several vacuum funnels at one time using only one vacuum pump. It's just a convenient way to operate several vacuum funnels at once. Now, in our picture here, we show a few different types of vacuum funnels for illustrative purposes. In most applications, the customer will be using the same vacuum funnel in all three positions.
Great. Another question, what are the options for testing nanofiltration custom filters?
I'm not certain what they're asking us in terms of maybe us testing them in-house. Probably fairly limited. You can certainly follow up with us by email and we can discuss what we could do.
Yeah, sounds good. Okay, let's see, what's the next question? Do you happen to know, Steve? Oh, okay. Glass fiber membranes versus nylon for filtration. Do you know which one would be best for filtration of water samples to limit organic addition for organic profile applications? I'm not sure if you're...
Yeah, I think they're concerned about maybe extractables from the polymer membrane. Glass fiber would certainly have very few organic extractables, binderless glass fiber, to be specific. There are some fibers, glass fiber media that have an acrylic resin binder, which probably wouldn't be good for that application. But binderless glass fiber would be. The challenge becomes what pore sizes retention do you require? Most of the glass fibers are nominally rated, and the smallest ratings go down to about half a micron. And in reality, those would be absolute rated somewhere around 1 or 2 microns. So if retention below, say, 2 microns or absolute retention below 2 microns is required, then you would have to consider a membrane. If absolute, if organic extractables are a real concern in the application, then you could consider an inorganic membrane like our silver membrane, which wouldn't contribute any organic extractables. Otherwise, those can be quite expensive, and otherwise nylon or PES could probably be evaluated. And they would just have to be characterized as blanks to make sure that whatever extractables come off them are not affecting the results.
Great. Good. What type of filter should I use for filtration of air that is input into a bioreactor?
Yeah, air filtration, you typically want to use a hydrophobic membrane, as I'd mentioned during the presentation. This is because they're resistant to wetting, and if the membrane structure is wetted, then it won't allow air to pass. The liquid within the pores won't allow air to pass. So hydrophobic membranes are used for venting. If you're worried about microorganism retention, then I would recommend a 0.2 micron pore size, most likely a PTFE membrane or polypropylene membrane for that application. The size of the filter will depend on the required airflow. And I did want to note that they may want to choose to pre-sterilize the filter prior to use, just to make sure they don't add contaminants to the reactor.
Great. Let's see. We've had a question about what kind of membrane is most appropriate for membrane distillation. Would you like to take that?
Yeah, we could talk about that as well. So obviously, hydrophobic membranes are also used for membrane distillation, and the membrane that would be used is dependent upon the process conditions, including the surface tension of the fluid, and the applied differential pressure on the membrane. Usually the differential pressure is minimized so that the membrane isn't inadvertently wetted, but depending on what's present in the feed stream, if this surface tension is too low for conventional membranes, we might want to consider using a membrane that's been treated to retain lower surface tension liquids, and those membranes are described as oleophobic, which we didn't discuss in the presentation, but they are available from us.
Great. This is a follow-up to a previous question, an input from someone else listening. It's for the person filtering silica. We use 0.45 hydrophilic PTFE membranes to filter out silica for microwave digestions of makeup, which works well. We sometimes start with the 1.0 membranes first and follow up with the 0.45 on a vacuum filtration system. So hopefully that's an additional help for that question. And thank you for contributing. The next question would be, which membranes, polymeric or ceramic, do you suggest for milk microbial decontamination?
So if it's milk samples, so small scale samples that are being studied in the lab, any 0.2 hydrophilic membrane would probably be sufficient. I would probably go with the 0.2 micron PES just because it might be challenging to filter that emulsion, which may tend to clog the membranes. In the PES, with its asymmetric pore structure, is more resistant to clogging. It has better dirt holding capacity than a symmetric membrane, say nylon, for example. For process scale filtration, it becomes a lot more challenging. I think large cylindrical ceramic elements are commonly used for process scale filtration of milk, but also there are polymeric cross-flow membranes that are used to process milk for removal and concentration of proteins and fats. And that gets beyond the microfiltration range that we discussed here, and also beyond my expertise, but those do exist. They're dairy cross-flow membranes. Mm. And if you can certainly reach out to us by email, and we have cross-flow specialists that might be able to help you more.
Great. Okay, for the nylon membranes, such as the 0.22 and 0.45 micron pore sizes, will the wetting time of the membrane depend on their pore size only, or will other parameters such as material and morphology characteristics play into that?
For the microporous membranes in general that are hydrophilic, the wetting times are usually, if not instantaneous, then certainly within 1 or 2 seconds, depending on the size of the filter. The wetting is a result of the capillary action, which is a function of the pore diameter. And for those very small, 1 micron and smaller pore diameters, their capillary action is actually very strong. So the wetting occurs very quickly, and it really doesn't change appreciably depending on the pore size, as long as the pore size is not, say, larger than 10 microns.
Okay. Do you have any information about useful life in the warehouse? So I think this is a question about best practices for storage and maybe expiration.
Yeah. We haven't done any formal shelf life studies on any of the membranes, but we have handled them and stored them and supplied them to users. And within my experience anyway, almost all of these membranes, if stored in in a sealed bag or the original packaging in a climate-controlled warehouse, can be expected to last for several years without any appreciable effect to their functionality or their performance.
Great. Okay. For protein separations, do you recommend to employ a microfiltration process previous to ultrafiltration?
It depends on the particle loading of the feed stream. Usually, if it's a small scale in a laboratory, microfiltration pre-filtration is not really required because the UF membrane obviously will retain particles as well as the proteins that they want to concentrate. But if they are worried about particle fouling in the feed stream or particle fouling of the UF membrane, then they could try a microfiltration pre-filter. Now, in process scale applications that are using spiral wound membrane elements to process the fluid, then microfiltration pre-filtration becomes very important because particle fouling can occur in the feed spacer that would plug the membranes and reduce their flow. And it's important to use microfiltration to prevent that from occurring.
Great. Let's just do one more question for now, and then I do encourage everyone, if you have additional questions, to reach out to us over email. Let me go back to that slide. You can always contact sales or info@sterlitech.com, or reach out to Steve or me directly with these emails. But for the last question, Steve, what membranes would you recommend for filtering a proteinaceous solution?
Yes, protein solutions can be challenging to filter, and that's because some membranes have affinities for binding the proteins, and while the capacity of the membrane to bind protein is usually very small, on the order of micrograms per centimeter squared, uh, that binding can cascade and result in plugging of the membrane pore structure, unexpected plugging of the membrane pore structure, and unexpectedly short service life. So for those applications, it's usually important to use a membrane that has low affinities for proteins. And within our product offering, the PES membrane or the cellulose acetate membrane or the hydrophilic PVDF membranes are all very good options for filtering proteinaceous solutions and have reasonable resistance to fouling and allowing those proteins to pass through the membrane unaffected.
Great. Wow. Thank you very much, Steve, for all of your insight. It's always very interesting hearing your input on these questions, and we hope everyone found it useful. Definitely follow up with us with any feedback on the webinar or additional questions that we didn't have time to go over. And thank you very much for listening. Hope you have a good rest of your day.
Yeah, thank you very much.